I realize that there's a great many interesting problems that I can solve using Newton's second law. If I can appreciate the nature of circular motion. Circular motion, even when it's motion with constant speed, is accelerated motion. Consider this object of mass m that moves in a circle here, and I've included the velocity vector on my diagram. If I tell you that it moves at 5 meters per second for the entire time going around the circle, that is motion with constant speed. That is uniform circular motion. I can calculate that speed as 2 pi r, the circumference of the circle, divided by capital T, the time period of the motion. If I asked you to calculate the acceleration, and you recall that the acceleration is delta v over delta t, you might have a hard time with that. We say, well, the initial speed is 5 meters per second, the final speed is 5 meters per second, so the change in speed is 0, so the acceleration is 0, but that would be erroneous, because velocity is a vector. It's an amount, a magnitude, and a direction. And as the object goes around in circular motion, the direction of the velocity vector changes, and therefore it accelerates. But in order to find out how much acceleration I get in circular motion, I'm going to have to be a little bit more clever. It's very often in our physics that I tell you that I'm demonstrating a skill that you must have. I am not, in this moment, demonstrating a skill that I expect you to have. I would love it very much if you could do the demonstration that I'm about to do using algebra and some careful thinking. That would be excellent. But you're not going to be expected to do it on your own. So please just try to follow the arguments, because what I'm doing here is convincing you that it's possible for me to calculate the magnitude of the acceleration of circular motion. So what I'm going to do is remember, inertia is the natural tendency of objects to persevere in their motions. So here I have this mass moving with a velocity v. If I do nothing to disturb its motion, that is, if I don't exert a force in order to alter its motion, it will travel in a straight line. So what I'm going to do is let it travel in a straight line. Imagine that this mass moves with this velocity. It'll continue moving here to the right, and I'll let it go out for a certain amount of time, say t, and then after that amount of time it appears out here, off the circular path that I intended for it to follow. In fact, the distance that it has traveled in that time is the speed v multiplied by the time t. That's the distance it's traveled in that time interval. But it's gotten off track. I wanted it to follow a circular path, but it didn't because I let it go in a straight line. What I needed to do was to have the object accelerate in order to change the velocity vector's direction in order to be on the circular path. So what I'm going to do now is make up for this mistake. By allowing it to go out here off track, now I'm going to let it accelerate back to the track. In order to do that, it's going to have to accelerate along this line directly toward the center of the circle. And it's going to have to accelerate for a distance x from here where it is off track down here to where it will be on track again. So by letting it go out in a straight line, I got off track. I said, whoa, stop. Accelerate back to the track with constant acceleration. Now we're back on track again. And when we come to that position, we find that we are similarly at a distance r from the center of circular motion. What I've cleverly done is to force this physical situation to reveal a right triangle. Human beings love right triangles. We love the math of right triangles, particularly the Pythagorean Theorem. The Pythagorean Theorem is great stuff. I have a right triangle here that has one side that is the radius, one side that is v times t, and a hypotenuse that is x plus r. So what I'm going to do is apply the Pythagorean theorem to this right triangle, such that r squared plus the quantity v times t squared is equal to x plus r, that quantity squared. That's the Pythagorean theorem applied to the right triangle that appears in my diagram. So I'm going to flesh it out a little bit. First, here on the right-hand side, the quantity x plus r squared, I'm going to FOIL that out. And when I do, I get x squared plus 2rx plus r squared. Again, on the left-hand side, I have r squared plus v times t squared is v squared times t squared. So what I notice immediately about this big equation that I have here is that I have an r squared that appears on the left and an r squared that appears on the right, such that if I just subtract r squared, from both sides of the equation. The r squareds are gone now. And I have v squared t squared equals x squared plus 2rx. Now, x is the distance that I let the object accelerate back toward the circular path with constant acceleration. Well, if I'm doing constant acceleration, I know that I can do kinematics. For example, I can invoke x is equal to x naught plus v0t plus 1/2 at squared. If I choose x naught as 0 and the initial velocity is 0, then the distance that I accelerate back to the curved path is 1/2 at squared. That's a kinematic argument. So I'll take that and I'll plug it into my equation wherever I see an x. Well, the first x that I see here on the right-hand side is squared. So 1/2 at squared squared is 1/4 a squared t to the 4th. Plus, I have 2rx. Well, that will be 2 times r, 1/2 a t squared. Obviously, those 2's, one in the numerator, one in the denominator, are going to cancel. Now, a little bit of simplification that I'm going to do is to divide both sides of my equation by t squared, just to get a little bit of simplification. Because when I divide the left-hand side by t squared, I just get v squared. When I divide the right-hand side by t squared, then 1/4 a squared t to the 4th becomes 1/4 a squared t squared plus r a times t squared, but t squared divided by t squared is 1. So what I'm left with is v squared is equal to 1/4 a squared t squared plus ra. It's quadratic in the acceleration. It's the acceleration that I wanted to find. So my equation for the acceleration is circular motion. At this point, hopefully, you find this a little bit vexing, because what is it that I've found anyway? I haven't found the acceleration of circular motion. I found the acceleration of going out horizontally and falling back to the circle again. And in order to continue, I would go out in a straight line now with a velocity vector tangent to the circle and fall back to the circle again. And then I would go out with a velocity tangent to the circle and fall back to the circle again, and go out tangent and fall back and go out tangent and fall back and go out tangent and fall back. I haven't found the acceleration of circular motion. I found the acceleration of this crazy ninja star motion. So I'm not terribly clear on how that was helpful. I found the acceleration associated with going around a pointy sort of star thing in the way that I've described. I'm not clear on how that's helpful, except it begins to become apparent to me that this is a useful way to proceed when I decide not to let it go off in a straight line so far. The reason why my diagram is so crazy pointy like this is that the time that I chose to allow it to travel out was so large that it got really off track. Don't let it get so far off track. Let it go for a shorter period of time. If I let it go for a much shorter period of time, I just go a little bit off track here, a much smaller distance, and then the distance I have to fall back again is quite small. And then I go off track again, and fall back again, and off track again, and fall back again, except this time as I do it, you find the triangles that are created are significantly smaller. Now, what used to look like a crazy star shape looks like a saw blade. Not a circle! But what if I made the time even smaller? In fact, what if I made the time so small that I can't use my marker to draw the little triangles? It would look like, when I drew it on the board, a circle. And you would say, no, Charlie, I still imagine that it's little triangles. It bothers me, little wiggles, little triangles. Okay, fine. I'll make them small. I'll make the little wiggles. I'll make the time so small that the little wiggles are smaller than atoms. You say, no, Charlie, it's still not the same thing. No. Okay, take that time and divide it by 1 billion. Not good enough? 1 billion again. 1 billion, as a matter of fact, 1 billion as many times as you like. It doesn't matter what you need to be satisfied. I can give it to you. So, I'm saying make the time infinitesimally small. So small that the time approaches 0. How close? As close as you want. As close as you get just gets better and better for me. It gets better and better and closer to a circle. Well, if t is approaching 0, when I examine my equation here, v squared is equal to 1/4 a squared t squared plus ra, the t only appears here in the 1/4 a squared t squared. Well, if t is going to go to 0, then that term is going to go away, which is very satisfying. Because then what I'm left with is v squared is equal to r times a. And I have found the acceleration of circular motion at constant speed. Rearranging the equation and solving for a, the acceleration of circular motion is v squared divided by r. That is the magnitude of the acceleration. Acceleration is a vector. It has a direction. The direction of the acceleration is clear to me when I look at my diagram. In my original diagram, I let this thing go off the circle and then accelerate back again. When it accelerates back again, it accelerates toward the center of the circle. This acceleration always points toward the center of the circle. Therefore, I call it centripetal acceleration. Latin enthusiasts among us will realize that the word centripetal means center seeking. The centripetal acceleration is the acceleration whose vector direction seeks the center during circular motion, always pointing towards the center. Notice that I've added a little subscript r to the acceleration, just to indicate that the acceleration that I'm talking about points in the radial direction. The acceleration points in the radial direction, the direction of the radius, which is towards the center of the circular motion. So the centripetal acceleration is v squared divided by r. All I need to calculate it in an instance of circular motion is the speed. Lucky for me, the speed of circular motion is relatively easy to calculate. It's simply 2 pi r, the circumference of the circular motion, divided by the time period, the time it takes to execute the circular motion. So that speed squared over r is the centripetal acceleration. The speed has units of meters per second. When you square it, those units are meters squared per second squared. If I divide that by meters, I get meters per second squared. The units of it are acceleration, just as I expect. So now I have a way of quantifying what I already knew, that in order to move away from its otherwise rectilinear path, an object going in uniform circular motion must accelerate. And now I know how much acceleration. Isaac Newton has taught me that whenever I observe an object moving with an acceleration, that there must be some natural constraint or condition that is the cause of the motion. There must be some natural constraint or condition that is the cause of the motion. Forces cause acceleration. So when I observe centripetal acceleration, Newton's second law tells me that the sum of the forces that act in the radial direction. If the acceleration points towards the center of the circle, so too must the forces, because F equals ma. The acceleration is in the direction of the force. If the acceleration is towards the center, the force has to be toward the center, or potentially away from the center, as we'll learn as we apply this to the problem. So, the sum of the forces that are radial is equal to the mass times the radial acceleration, but that radial acceleration is v squared over r. We call this centripetal force. Centripetal force is not a new kind of force. I still have the same force list that I always had. Weight forces, push-pulls, tension, normal force, friction force, springs, rocket motors, viscous drag, buoyant force, whatever. Centripetal force is not a new force to add to the list. Any force can play the role of centripetal force. And when it does, it causes circular motion with an acceleration equal to v squared over r. A really quick example of this, just for fun, a quick application. When I have an automobile going around in circular motion, and this is going to be kind of a curious diagram because I'm drawing the automobile from the front. So this is my little punch buggy automobile, and it looks weird when I draw it from the, sorry about that. And it's got that little antenna that goes off the back. How strange. It looks like an angry beaver or something. But here comes the car, it's coming at you. And it's gonna go around in circular motion toward the center of the circle, which is right there. So it's gonna come out of the board and come towards you and curve around like this. What are the forces that act? Well, there is weight force, mg, directed downward. And there is normal force, directed upward. And there is friction force pointing towards the center of circular motion. In this case, the normal force doesn't point to the center. The normal force is not a centripetal force. The weight force doesn't point towards the center. The weight force is not a centripetal force. But the friction does point towards the center. When a car goes around a curve, it's the friction force that is the cause of that motion. You know this because you're not allowed to drive in the snow. The reason why is that when there's snow on the roads, the coefficient of friction goes way down, and the friction force goes way down. When the friction force goes down, a car can't or is less likely to successfully make turns, circular motion, because there's less friction force available. So if I apply this using my Newton's second law, the centripetal force is the friction force, which means in this case, not all cases, come on. In this case, it's the friction force that plays the role. Again, centripetal force is not a special kind of force. Any force or combination of forces can play the role of the centripetal force in circular motion. But in this case, the friction force is equal to mv squared over r. So, since the friction force is equal to mu times the normal force, and I have lots of experience solving Newton's second law problems, so I can look at this free body diagram now and realize that the normal force is equal to mg, then that friction force, which is mu mg, is equal to mv squared divided by r. Look, the mass cancels, and that's lucky, because some cars are very massive, and some cars are very, I don't want to say light, because that implies weight. I've asked you before, what's the opposite of massive? I don't know. It's very wee. Less massive. Less massive. And so applying here, the coefficient of friction multiplied by g is equal to the speed squared divided by the radius. Well, whenever I have cars going around curves, you usually don't get to choose the radius of curvature of the road. You don't usually get to choose the coefficient of friction, mu. You don't get to choose what planet you're on, so you don't get to choose g. What you do get to choose is the speed that you travel. And based on the coefficient of friction, there's a limit on the speed. So I can use my physics now, my understanding of Newton's second law, and how it applies to uniform circular motion to solve problems that are much more interesting than some of the problems I've solved before.